Page 352, the solver for solving polynomials. We've been calculating the pH of various acids and bases using the quadratic formula, using successive approximations, and circular reference. Let's do it now using the solver and or goal seek. So previously we calculated the pH of a 0.1 molar solution of periodic acid. With a Ka of 0.0229, we obtained a pH equals 1.423. Recall that the hydrolysis equation of an acid and water can be rearranged to x squared plus Ka times x minus Ka times Cha equals 0. So let's obtain the positive root. That'll be the hydrogen ion concentration, x in this case, using the solver for the equation x squared plus 0.0229x, 0229 is the Ka of periodic acid, minus 0.0229 times Cha, again for periodic acid, 0.1 molar. Let's go to the spreadsheet and take a look at this. This Excel file is named pH exercise, and the worksheet is labeled polynomials. Our quadratic equation is ax squared plus bx plus c equals 0. In column B I have labels. In column C I have the values. In cell C3 I have the concentration of periodic acid, 0.1 molar. In cell C4 I have the coefficient A, which is 1. I don't really need this term. I could have left it out, but for completion I include it. In cell C5, I have the value of Ka, which is the coefficient of x in the quadratic. 0.0229 is the Ka of periodic acid. In cell C6, I have the constant C, which is minus Ka times Cha, and I have it as a calculation. Here's the formula, equals minus C5, which is Ka, times C3, which is a concentration. Cell C7 contains our quadratic equation, equals ax squared plus bx plus c. I've used references to various cells. A in the quadratic refers to cell C4, which is 1. This could have been left out, times x squared. Now x is in cell C8. This is the concentration of hydrogen ion that we'll be solving for. I've just given a nominal value to start with. Just let it be 1 or some value that's positive. Plus b times x. So b is in cell C5. That's the Ka value. And again, x is in cell C8. Plus our constant, which is in cell C6, it's minus Ka times Cha. In cell E8, I have a formula to convert the hydrogen ion concentration to pH. So we're all set to go. We're going to run the solver. You could also run goal seek, either one. I'm going to run the solver here. To run the solver, on the Data tab, choose Solver. We'll set the objective, which is cell C7. It contains our equation, to a value of 0. Recall the quadratic is to be equal to 0 to solve for its roots. By changing a variable cell, our variable cell is cell C8. This is the hydrogen ion concentration that will be varied or changed until the equation in C7 equals 0, as we've asked. We'll apply a constraint that the value in cell C8 is greater than or equal to 0. So we click Add, Cell Reference, C8 is greater than or equal to 0. We can only have positive concentrations, never negative. Say OK. Make unconstrained variables non-negative. I think that's irrelevant here since we've already constrained it. we're going to choose GRG nonlinear, which is suitable for nonlinear functions, as in this case. Before we click Solve, let's explore a couple other options. On the Options tab, under All Methods, set the precision constraints to some small value. 1e minus 15 is very small. Select Use Automatic Scaling. Set the integer optimality percent to 0.1% or less. Set the solving limit maximum time to 100 seconds. That's plenty long to wait. Or the maximum iterations to be 100. We're going to use GRG nonlinear. On that tab, we'll set the convergence again to the same value, 1e minus 15, or some very small value. Leave the rest of the settings as default and say OK. And we'll solve. The solver has found a solution. Let's check it out. So we're told that when the equation reaches a value of 0 or very close to it, the hydrogen ion concentration is 3.78 times 10 to the minus 2, and that pH is 1.423, which is the same value we obtained using the quadratic formula or other methods earlier. The solver can be used in similar fashion to solve higher order polynomials like cubics or fourth order polynomials and so on, and the examples are shown in the Excel worksheet. Page 358. Let's look at one last example of an iterative process tool like the solver or goal seek. Equilibrium concentrations and the Haber process. So consider the reaction. 2 moles of ammonia produce 1 mole of nitrogen and 3 moles of hydrogen. The equilibrium constant for this reaction is 0.095 at 650 Kelvin. Now the Haber process was developed in 1910 in Germany to fix nitrogen. So nitrogen and hydrogen react to produce ammonia. It still is the #1 in the world industrial process for fixation of nitrogen to produce ammonia for, say, fertilizers or explosives. In this application, we will assign some initial concentrations to the 3 species and then calculate the equilibrium concentrations of the species. The reaction is in equilibrium and so can move in either direction. But if we give it a large initial concentration of ammonia on the left, we can be assured that the reaction will proceed from left to right. Now we don't know how much of the ammonia will dissociate, but for every mole of ammonia initially present, we can say that X moles of it dissociates. And since we start with 2 moles of ammonia, we can say 2X moles of it dissociate. We write the change in concentration as minus 2X, and therefore the equilibrium concentration would be the initial concentration 2.5 minus 2X. For every 2X moles of ammonia that dissociate, 1X moles of nitrogen is produced. So the equilibrium concentration of nitrogen would be the initial concentration of 0.1 molar plus X, or 0.1 plus X. And again, for every 2X moles of ammonia that dissociate from the balanced equation, we can say that 3X moles of hydrogen will be produced. If the initial concentration was 0.3 molar, the equilibrium concentration is 0.3 plus 3X. So we have the equilibrium concentration of all 3 species. We can put them into the equilibrium expression, nitrogen times the molar concentration of hydrogen cubed divided by the molar concentration of ammonia squared. Here are the terms. We'll set that equal to the equilibrium constant of 0.095. So we have one equation with one unknown. It's a great application for one of our iterative solvers, such as goal seek or the solver. Let's look at the spreadsheet to see how this is done. This Excel file is called pH exercise. The worksheet is called Haber. In cell B38, I have the equilibrium expression typed. So just recall again, here it is, molar concentration of nitrogen times the molar concentration of hydrogen cubed divided by the molar concentration of ammonia squared. So that'll be for nitrogen, it's 0.1 plus x, here it is, times, for hydrogen, it's 0.3 plus 3x, and that term is cubed. For ammonia, it's 2.5 minus 2x, and that term is squared. That's what we have typed here, 0.1 plus x. Now x refers to cell A38, and you'd give it some number to start with. I just gave it 0.1 as a number to work with. We'll refine it. The solver will find, we hope, the exact value for x to make this equilibrium constant equal 0.095. The second term here is 0.3 plus 3x cubed. There it is. And that's the hydrogen concentration at equilibrium, 0.3 plus 3 times x cubed. There's x. Divided by 2.5 minus 2 times A38. For ammonia, recall, it's 2.5 initial concentration minus 2x, and x is A38. That term is squared. So we'll run the solver and tell it to set the value of this equation equal to the equilibrium expression constant 0.095 by changing this concentration. Furthermore, whatever concentration is in cell A38 is being used in the calculation of the final concentration, the equilibrium concentration of the species. So here in cell B38, I've typed in 2.5 molar minus 2 times the value of x. This is in cell A34. And then the sum of these two gives us the equilibrium concentration of ammonia. For nitrogen, the initial concentration is 0.1 molar. The change is equal to x, right? Here it is. And that's cell A38. And the sum of these two gives us the equilibrium concentration of nitrogen. In the case of hydrogen, the initial concentration is 0.3 molar and has a change of 3x. So here I have equals 3 times the value of x, and the sum of these two gives us the final equilibrium concentration of hydrogen. I think we're set to run the solver. Go to the Data tab and choose Solver. We're going to set as an objective the cell that contains the equation that has to be solved. That's cell B38. It's already there. We're going to set that to a value of what? Not 0. We'll set it equal to 0.095, which is the equilibrium constant. And for that to be true, we're going to ask the solver to change cell A38 to find the value of x that makes the equilibrium expression equal 0.095. You can see it isn't equal to it now. This is not the value of x at equilibrium. The only constraint we'll apply is that the value in cell A38 has to be greater than or equal to 0. And I'll show you how that's done. We'll delete that and we'll add a constraint, and we'll say the constraint is that our x value, cell A38, must be greater than or equal to 0. We have positive, not negative concentrations. We're going to choose the GRG nonlinear because there are cubes and squares in this expression. It's certainly not linear. We don't need to make further constraints. We've already made the specific constraint here. Let's try solving it. The solver says it found a solution. Let's take a look. Well, sure enough, the equilibrium expression now is equal to 0.095, and to attain that, x was set to 0.245 molar. So by subtracting minus 2 times x and then combining that with the 2.5 molar, we find our equilibrium concentration for ammonia is here. Likewise, the equilibrium concentration for nitrogen and then for hydrogen. So it's pretty easy to use, pretty powerful tool. It's certainly worth being familiar with. page 360 to page 362, differentiation of a titration curve to find an endpoint. I'm going to go directly to the Excel spreadsheet because I think it's easier to explain there. This Excel file is called Differentiation, and the worksheet is called Acidometry. Here is data from a titration curve. HCl is being titrated with sodium hydroxide and a burette. We're using a pH meter rather than a visual indicator to monitor the progress of the titration. There are times when it is advantageous or necessary to use a pH meter rather than a visual indicator, as for example if the solution is so darkly colored that you can't see a color change. Or perhaps if you don't know what acid or base you're titrating, you really don't know what the pH is at equivalence point. In such a case you would run a potentiometric titration like this. So notice that initially the pH is acidic, as would be expected since it's HCl. Increments of base are added. Stirring is usually used. As soon as the pH meter stabilizes, a reading is taken, and a second and third and fourth and fifth increment of the titrant is added. And this data is plotted to find the endpoint of the reaction. And the endpoint is the point where you have the greatest slope, the largest vertical inflection, the largest pH change for a small increment of titrant. So we can estimate by looking at this curve that the endpoint is somewhere between, say, 15.5 and 16-ish. But we can do a better job of identifying the endpoint more precisely if we do what is called a first derivative plot. So looking at the curve, we see that the slope increases most rapidly, or the slope is the greatest at the endpoint. If we plotted the slope of this line versus mils of titrant, the point where the slope is the highest would be the endpoint, and we could see that best with a first derivative plot. So how do we do that? On this blue graph, we'll plot the change in pH per change in mils. So the rate of change of pH with respect to mils of titrant is actually the slope of this plot. And we'll plot that versus the volume added. So let's get those changes of pH to begin with. So this point is the difference in pH between two consecutive pHs, C6 minus C5. Let's drag that formula down to see how that works. The next point is the change in pH between the next two consecutive points. We'll drag that down again. This point is the change in pH between the next two consecutive points, and so on. So we can just autofill that to the bottom. We want to divide the change in pH by the change in volume. So let's get some change in volumes. The change in volume is the difference in volume between two consecutive points. So between 2 and 0 in this case. We'll drag it down and look at the next point. This is between the next 2 points, 4 mils to 2 mils, and so on. One more time here. The change in mils, or change in volume added, B8 minus B7, and so on. We can autofill that. All right, so we want to then get the Y values are delta pH over delta mils. So we have that here. It'll simply be E6 divided by D6 for our first point. Our next point will be E7 divided by D7, change in pH over change in mils. And so on. We can autofill that. So that'll be what we plot on the y-axis. Now on the x-axis we want to plot the volume, but what volume will we plot? Since the change in mils was taken over two separate volumes, we're going to plot the average of 2 points. This will be the average, or the midpoint, of 0 and 2, which will be 1 mil. How about the next x-axis point? It'll be the average of the next 2 mils of titrant. Between 4 and 2, the midpoint will be 3, and that's the average. We can autofill that down. And when we do that and plot the change in pH per for change in mill, which is really the slope of this line, versus the midpoint of the mils of titrant added, we can see that immediately before the endpoint, the slope rises sharply. It's positive and strong. At the endpoint or equivalence point, the slope stops increasing and abruptly starts decreasing. Our best estimate here of the endpoint of the titration is again somewhere about 15.7 or 15.8 mils. And that's a first derivative plot, the change in pH with respect to mils versus the mils added. We can do one better than a first derivative plot. We can do what's called a second derivative plot. So instead of plotting the slope of the original titration curve versus volume, we can actually plot the slope of the first derivative plot versus volume of titrant. What do we expect to see? Well, the slope of the first derivative plot is fairly constant, and then goes sharply positive, levels out, and then suddenly plummets negative. So the equivalence point could be identified as the point where the slope goes from strongly positive to strongly negative on a second derivative plot. So we're going to plot the rate of change of this slope with respect to mils versus mils of titrant added. So here we'll have the change in the slope between two consecutive points. Let's get the next point. That's the change in slope between G8 and G7. Remember, this is slope, and we're measuring the change in the slope. And we'll just autofill that down. We want to divide that by the change in milliliters that corresponds. So this point will be the difference between two consecutive volumes, in this case F7 minus F6. Let's get another point. The difference in milliliters is the difference between two volumes. Let's autofill that. Alright, so we're ready to calculate this change in slope with respect to volume. That'll be our y-axis value on the orange curve. That'll simply be the change in slope divided by change in mils. I7 divided by IH. Let's get the next point. This is I8 divided by H8, the change in slope divided by change in volume. Enter. We can autofill that one down. Now we're going to plot those values on the y-axis of the second derivative plot against the volume of titrant added. But what volume? We're going to take the averages of the two previous midpoints, F7 and F6. Let's get the next point. This would be the average of F8 and F7, and so on down to the end. We'll autofill this, and we plot the data, and notice what's happened here. The rate of change of the first derivative line, or the slope of the first derivative line, is relatively flat. It becomes strongly positive and increases, and then it plummets through the 0 point and goes negative, and it's the 0 point which is equivalence point, and we can read that as approximately 15.7 or whatever you wish. Now if you want to read this more exactly, you could replot this and expand the graph. Here I've expanded the plot in the range of the endpoint for the first derivative plot and the second derivative plot. I don't know if that makes it any easier. Looks like this is probably 15.6 something, and this point of intersection on the second derivative plot is 15.7 or 0.8. The moral of the story here is that the more small increments and measurements you can make near the endpoint, the better will be your endpoint detection for these differentiation plots. So just to recap, acid-base reactions can be monitored with a pH meter instead of or in addition to a visual indicator. Other types of titrations like a redox titration can be monitored. Here, a solution of hydrogen peroxide is being titrated with potassium permanganate, and the progress of the reaction is being measured using a platinum electrode and calomel reference plugged into a multimeter which measures millivolts. And after each small addition of the titrant, the millivolt reading changes and you can get a beautiful titration curve which can then be refined with a first derivative or second derivative plot. So this is a very handy technique. It should be in the arsenal of every technology student going into industry.